So good on you.
Which shows our sensitivity.
So, yesterday's lesson showed us a famous result, the Michelson-Morley. They were trying to attempt to determine the speed of the ether because they thought that light needed a medium. Turns out it doesn't. Maxwell said light doesn't need a medium. It's self-propagating. It travels through an electric and magnetic field. But the important thing was the fact that there was no interference patterns suggested that the light was not changing due to travelling upstream and downstream when the Earth was 6 months apart, travelling in opposite directions. The interferometry didn't show any interference. So Einstein took that and said, well, it might be that the speed of light is constant for all observers, irregardless of their motion relative to the source. So we spoke about this. This is a very strange thing. If you were on a skateboard traveling forwards at 4 meters per second and you threw a baseball forward at a speed of 3 meters per second, then somebody outside in a different frame of reference would see the ball traveling at 7 meters per second. That is classical relativity. All right, so that works. What does not work is light. So now let's imagine that we had an imaginary skateboard that could travel at relativistic speeds. Let's say v equals 0.4 times the speed of light. You're going to see this kind of notation commonly. You'll express your velocity as a decimal value of the speed of light. Let's say you then get your laser pointer out and you fire a beam. Ooh, let's drop that down a little bit. At the speed of light. Well, this is where it breaks down. The observer does not see 1.4c. That is incorrect. And so the Michelson-Morley experiment suggested that all observers see this bloke here sees it as the speed of light. It doesn't matter your motion relative to the source. Okay? There can be phenomena such as Doppler shift. So you can get blue shifting occurring if it's traveling towards you, red shifting if it's receding. This brings up his two postulates. Again, different textbooks have the two postulates written differently. You have to rote learn them, all right? Doesn't matter which one you rote learn as long as you write them down correctly. So the first one was the Galilean Relativity that says that, what does it say? No reference frame can be considered greater or truer than another, or no one can identify a reference frame that has absolute rest. All right. In other words, no single inertial frame of reference is better than another. That basically says that when you make your observations, yours are correct in your reference frame. The other one then is the speed of light is a constant for all observers, irregardless, add that last bit at the end, irregardless of their frame of reference. Okay? So you'll never be able to see anything traveling faster than c. And in fact, the only thing you can observe traveling at the speed of light is light. You cannot see particles traveling at the speed of light. So just remember they need to be rote learned. So practice writing down your definitions, and you might be tested on, what postulate does this experiment explain, or what, this experiment explains which postulate, or which postulate is required. Now, an interesting thing occurs. Due to the finite nature of light, the invariance of light, it is the speed of light for all observers, we get this issue of simultaneity, or at least simultaneity does not exist. I just want to show you this animation. It's a very slowly moving animation. We'll wait for it to load up. Here we have, come on, why have you frozen? Here we go. Here's three different observers in different parts of space. Now, from our frame of reference, these two events occurred at the same time. If yellow is equidistant, then watch, he goes, yep, I see red and green. Boom, I saw them at the same time. But hang on, The blue guy goes, no, I saw red. The grey guy goes, no, I saw green. And he goes, I saw green, and then I saw red. And the blue guy goes, no, I saw red, and then I saw green. Well, this is a problem. You've got 3 different observers in different points in space making different observations. The bloke in the middle said it happened at the same time. The blue guy said, no, I saw red first, then green. And then over here, I saw green first, then red. If light travelled infinitely, then you would say, all 3 would say they happened at the same time. Now you could say that these 3 observers are all in the same reference frame. They're all stationary relative to the sources, but they're in different points in space. And so it takes time for light to travel. Okay? So, this is an interesting consequence of simultaneity not applying due to light travelling at a finite speed. I want to bring in our first sort of thought experiment. Imagine Einstein thought about trains that could travel at very fast speeds. So you'll often hear about the Gundankan Train, which is basically the thought experiment of a train. Now, in this first one, let's just suppose that our 2 observers are both, they're both at the same speed, stationary, and 2 lightning bolts strike either end of the train. Okay. In this case, you're setting up the length of time. Oh, let's just draw straight lines here with our... Great. The length of time L1 and L2, they're the same. So this guy would say, yep, it happened at the same time. Both observers would agree that these 2 events occurred simultaneously. And in fact, the bloke, well, let's just take this as L on 2, and this one here as L on 2. And yep, this guy here could somehow make a measurement that T equaled L on 2 times the speed of light. T1 equals T2. We're all in agreement. Everything's nice and symmetric. We're happy there. They would both agree. You would say, did you see the lights at the same time? Yeah, yep, I saw the lights. They both flashed at the same time. Now, let's kick things up a notch. Let's have this train now travelling relative to observer number 1 at some speed, okay, v. Now, the lightning strikes each end of the carriage, and this bloke here, I'm just going to draw, well, it's already drawn for us. Let's just have a look at what this guy sees. The light would travel to this guy the same distance. The time taken would be, well, L on 2. We'll ignore any vertical dimensions. We'll just imagine the horizontal dimension in this scenario. So he said, yep, the lights flashed. They both travelled L on 2 at the same speed. T1 equals T2. This guy goes, same time. He would say that those 2 things occurred simultaneously. But in that time of L on 2 times C, the train has advanced forwards. I would like you to just draw a silhouetted train. In that time period, it's gone forwards. And in fact, I don't know why I'm stuck with this grey pen. Let's go here. The change in length is going to be the velocity multiplied by the time period. And so in that time, the back light has to travel a little bit further. So he would say, I saw the front flash first, and then a certain period of time later, even though he observes the light approaching him at the speed of light, because light is finitely traveling velocity, you've advanced towards the first source in a given time, and so obviously you're going to meet the first light first, the forward light first. You're going to then take a little bit longer. So this is a consequence of the invariance of light. Since light travels at a finite speed, 2 observers will not be able to agree on the order of events of when they occurred. Okay? Now, simultaneity gets tricky. Not sure whether it might appear in the WACE exam, but I just wanted to cover that in case it appears. Now, I'd like you to help me derive the Lorentz factor. Now, this is a factor that makes sure you don't break any of the rules. So could we please go over the page? Oh, hang on. Let's go to page 13. No, 14? Hendrik, there he is. All right, here is Hendrik Lorentz, a famous mathematician. It was named after him, but it was basically Einstein that was doing all the hard thinking. So we're going to set up another Gundankan experiment. There are lots of different derivations of the Lorentz factor. Let's suppose we have a train that can travel really fast with some speed v, okay? And the train has a height, call it L0, okay? And inside the train, there's an observer that observes a beam of light, like a laser beam, travels up a certain distance. Now, that distance can be measured as c times t naught. Now, t naught is called the proper time. We're going to have two different times here. Remember, you've got two different observers in two reference frames. I'm going to bring in the second observer in a moment. But if you are in the same reference frame as the event, that is, we're all in a train right now, and we're all racing towards Fremantle at 0.85 the speed of light, all right? And so there's a laser, and the laser shoots a beam up to the ceiling, and you measure the time that it takes. Since you are in the same reference frame, you are measuring t naught, the proper time, or stationary time. So let's just write a few things down, or stationary time, meaning you are in the same reference frame.
Of the event occurring.
That's it. Okay, same reference frame. Now, let us look at an observer that's in a different frame of reference. And to make this make sense, that they're both going to be observing the beam of light with their stopwatches. So the bloke on the train, he measures the proper time. The bloke outside, he's going to measure a different time. He's going to measure a moving time. So could we just write over here, t equals measured time in different reference frame. And these are inertial reference frames, mind you, constant speed. We don't care how the train accelerated up to that speed. We just said, imagine, zoom, it races past, and just as it goes past this bloke in the red, boom, there's a flash of light. Now, the bloke in red is going to observe that the beam of light doesn't travel vertically, it travels on the horizontal. And in fact, this side length here is going to be v multiplied by his observed time, t. Okay? The light that he sees has a length along the hypotenuse, and that's going to be the speed of light times t. So you can see two dimensions now have been brought up by the observer outside. He sees the adjacent being produced and the hypotenuse. The bloke inside the train doesn't know about that. He just goes, all right, I just saw a vertical line. What this has done has brought up some Pythagoras. Now, this is the simplest way to show the Lorentz factor. We're going to bring in the Pythagorean theorem. Let's just redraw our triangle. We've got CT, we've got VT, and then we've got the T naught as CT naught. So, let's just square both sides. By the way, you do not need to show the derivation. I just think it's a nice little nifty thing to show from two different observations. So CT naught squared plus VT squared equals our hypotenuse squared. Okay, so C squared T naught squared plus V squared T squared equals C squared T squared. Could we now just divide everything by c squareds? And we'll be able to cancel a couple of things. but we can't cancel out the v squared t squared one. So let's now say, all right, I've got t naught squared plus v squared on c squared t squared equals t squared. What am I going to do next? I'm going to get my t naught squared on its own. So that's going to be t squared minus v squared on c squared t squared, all common factor. So I might factorize out my t squared term. All right. And then lastly, we want to express the observed time in terms of your proper time. And then we want to get t, not t squared, so we'll take the square root. Well, you know what I'm trying to do here, take the square. So finally, we get that your observed time is equal to t naught over the square root of 1 minus v squared on c squared. It is though the two times are different by some factor. And we're going to take that factor out. That is the Lorentz factor. And we'll look at its shape and its limits of, what it can and cannot be outside of. Yes, Ethan?
So what was the equation's name again?
This is the Lorentz factor to show time dilation. Now, here is the problem. Einstein's second postulate said that the speed of light is travelling at the same rate for both observers. But if there's relativistic motion, i.e. getting pretty fast, then we get a problem that one side length is now the hypotenuse, the other side length is the adjacent. And so in a given time that this guy's observing, it's going to get a certain length. If I rotate that around, it hasn't gotten the full length yet. So the only way that these two things could sync up is if this guy was to observe this happening in a certain time. It hasn't gotten there yet. It's going to have to be travelling slower. Now, I've just had a brain fart here, but in order for this to work, if the speed of light is constant for both, for this to happen in a time period, that had to happen slower. Okay? So now imagine the two stopwatches travelling along at the speed of light. If this guy's travelling a longer distance in a given time period defined by the speed of light, then this one must be travelling at a little bit slower. And you can figure out, at what proportion. You can do some trigonometry. The easiest way to understand this phenomena is that when you observe a moving clock, it is seen to tick slower. Okay? So if you we'll put this down first and we'll take an example and see the consequences. It's a bit weird, but in your data sheet, this is what you have. All right, so just recall data sheet, it is given. You don't need to derive it, but let's just take out what's happening. We've got that your observed time is your proper time multiplied by some factor. We're going to call it gamma, where gamma is known as the Lorentz factor. And I always get his name wrong. It's 1R. And this Lorentz factor is 1 over the square root of 1 minus v squared on c squared. So I'd like us to just calculate. Let's just do a quick calculation now on this side if you've got the room. Let's now just put some values in. Let's say that the train was travelling at 0.85 times c, so 85% the speed of light, okay? And the bloke on the train observed t naught equal to 1 nanosecond, okay? So the proper time was 1 nanosecond. That's how long it took. We could figure out the height of the train if you wanted to. Just rearrange your constant velocity equation. So let's just throw down here. Now, if v equals 0.85 c, the easiest thing to do, gentlemen, don't leave it in meters per second, because it's a nasty looking equation. Write it as v on c. In which case, v squared on c squared is just 0.85 squared. The maths becomes a lot simpler. I don't want you to be daunted by all these brackets and scientific notations to the square. Oh, it's on a fraction. No, you can just express v squared on c squared as 0.85 squared. We'll take our t0 as 1 nanosecond. So, while this clock the clock reached the ceiling, it's now a clock that's travelling at the speed of light, and so our stationary observer measured that when the stopwatch smacked the ceiling, it read 1.0 nanoseconds. But the person outside of the train, this is very weird because we don't experience this. It's strange. It doesn't make sense. Someone outside with a telescope watching that clock, as it's travelling up, it's travelling slowly. And by the time it gets up there, it's actually read a longer time. Okay? And so let's measure what that observed time is. It's going to be t0 over the square root 1 minus v squared on c squared. It's going to be 1 nanosecond over the square root of 1 minus 0.85 squared. That's a lot easier to write into your calculator. Okay? And so out spits 1.90 nanoseconds. Now, I think I might have said something that wasn't quite correct. We're watching, imagine you're outside and you're watching this photon of light that has a stopwatch and you're looking at it through a telescope. It's ticking slowly. You're looking at your stopwatch outside and it's reading 1 nanosecond. It hasn't yet gotten to the top. It's only reading half a nanosecond. You're looking at your stopwatch in the red, it says 1.5. You look, it hasn't yet reached the top, it's reading 0.8. You look at your stopwatch in the red, it reads 1.9 nanoseconds, and you see that the stopwatch, when it hits the ceiling, it reads 1 nanosecond. Okay? So that's the two different measurements in different reference frames. Yes, Budge?
How do you call one time the proper time? Like, how do you, because
yeah.
the opposite happen with the other person?
So if we both watch something in this classroom, we would both be measuring the proper time. We're in the same reference frame. If somebody went whizzing past it, so imagine you just throw a ball up and you measure the time taken for the ball to go up and down. Light beams are better because it's common, the second postulate says. So we bounce a beam of light, boom, boom, we measure the time. Someone whizzes past. Well, they don't see boom, boom. They see boom, boom. They see a triangle. And so all of a sudden that light has travelled a longer distance. Now, in order for that light to travel a longer distance, its clock must have been ticking slower. And so that person whizzes past and goes, hang on, that was 1.5. So we're going to combine length and time in just a moment. Yes, Lucas?
So this equation only works for things that are travelling at the speed of light?
Close to. So, okay, let's just look at the Lorentz factor. Hold on. Our Lorentz factor only becomes significant when the speeds get really, really fast. I'm just going to rewrite the factor over here again. 1 over square root 1 minus v squared on c squared. When v is small and you express it as a decimal and then you square it, it gets even smaller. And so 1 minus a small number is still pretty close to 1. And then you take the square root. So it's still going to be close to 1. Have a look at this. This is the Lorentz factor. You can see here, you cannot get a square root of 0. So v will never be able to equal c. As v approaches c, your Lorentz factor, it asymptotes to infinity. This basically keeps us from breaking the speed limit. It prevents anything travelling at or greater than the speed of light. If you try and put in the speed of light, then our time, observed time, would approach infinity. That clock would start slowing down so much that it would be stationary. Now, we don't want to talk about what happens at C because it can never get there. Now, it becomes significant at around about, well, we're going to calculate it. Could we just skip over a couple of pages? There's a page that says, at what speed does it become significant? Could you tell me what page that is? 20? All right. Come on, little laptop. I know you're struggling. All right. Guys, does the top of page 20 have a couple of lines? Okay. I'm just going to start writing somewhere on the page. Stupid bloody laptop. Remember I told you 10%? That was when we have to consider relativistic effects. So what I'm going to set here is T0 as 1 second, and then I'm going to set your observed time to be anything greater than 1.005 seconds. What that means, if anything was greater than that, we would have to round that number up, yeah, and then that would make it 1.01. That would be significant to the third figure. Now, this is basically picking apart the Lorentz factor. It involves a lot of reverse BIMDAS. If you're good at arithmetic, it shouldn't be too hard. There's 3 things that you could be asked for. You could be asked for T. That's easy. We just did that. You could be asked for T proper or T0. That's easy. Just rearrange. The hardest part would be what speed must you be traveling such that T0 equals that and T equals that. So let's put the equation down. We'll go T equals T0 over square root 1 minus V squared on C squared. The end game is, what is V on C? Okay, that's what we want to pick it apart. So, all right, let's divide both sides by T0. Let's square both sides. In fact, I'll do it down one step. And and we can also flip it. So I'm just going to flip it, T0 over T. Now you could keep leaving it in general form. Actually, I did, so let's just keep leaving it in general form. I'm going to go 1 minus, so subtract 1 and then multiply by -1. I'll get V squared on C squared equals 1 minus. And then I might take the square root of both sides. It looks very similar. And I might evaluate it there, and let's see what our V on C equals. So let's go square root of 1 minus 1 on 1.005 all squared. We get 0.996. That is that V equals 0.996. That is velocity equals 0.996c, or roughly 10% the speed of light. Okay, so anything faster than that, your observed time now becomes 1.1 seconds. That's significant. So just keep that in mind. If you ever see values where the velocity is less than 3 times 10 to the 7, theoretically you shouldn't need to worry about it. I think I've thrown in a question, and there was a question in last year's WACE, I believe it's at the bottom of your page, that says, show why speeds of 100 kilometers per hour do not require relativistic effects. Well, you're basically saying convert your 100k into 27. You're saying 1 over the square root of 1 minus 27 on 300 million squared. It equals 1.000000000. I don't think your Casio calculators will actually give you. All right, quick, do it. Let's see if your Casio calculators do it. I want you to do the Lorentz factor for the question in last year's WACE exam at the bottom of the page. I just want you to show me that the Lorentz factor is so close to 1 that it is not funny.
Yeah, it just says 1.
It says 1. So your calculator won't even show you what figure the Lorentz factor exists at. Okay? Now, there were multiple ways of saying it. You could say that, V on C is so close to 0 that the Lorentz factor ends up becoming 1. All right? So it is not significant. So that's why if you watched somebody's clock as they zoomed past you in the car, imagine they held up a stopwatch and it's running, and you watched it with a telescope, it would be slowed by a factor of 1.00000000. You wouldn't even be able to detect how much it slowed down by. Budge.
Does the person on the train see everything outside something faster?
Slower.
It's the same for them,
It's
right?
paradoxical. So this is the whole thing, boys. Budge has brought a very important question. The person outside the train sees the clock inside the train ticking slower. The person inside the train looks out and sees the person in red, their clock is ticking slower. This is the issue of simultaneity not existing. No.
How do you get to 1 point?
That's paradox. That's the paradox.
Because to them, they're the ones moving it. That's
Yeah. So the bloke on the train goes, no. I'm measuring your clock, and I'm seeing your clock tick slower. And this is where it doesn't work. This was the animation at the start. Simultaneity does not exist. That is why there are paradoxes that exist.
So will both clocks read 1 nanosecond when it hits the top, because his is going slower and yours is going at the right time?
Well, the bloke on the train reads 1 nanosecond and says, that's my... He would observe... His clock would be the opposite. His would be slowed down. So now you take T proper as 1 and then T will still become 1.9. So he would say, no. I saw your clock slowed by that factor, and they are not in agreement. Simultaneity does not exist when you're moving at relativistic speeds. It should be strange. It doesn't make sense. There's a paradox that I placed at the bottom of page 16. Yes, the twin paradox. Now, just have a quick read. If we stayed on Earth and one of the twins jumped on a spaceship, travelled away at 95% the speed of light to a distant solar system, 10 light years away. Okay, so that's going to take just over 10 years to get there, 10.5 years, and then turn around very quickly, come back, another 10.5 years. 21 years would have elapsed. Twin that stayed at Earth would have aged by 21 years. So a 30-year-old astronaut, he's now 51 and a half, and he's old and grey. However, twin number 2, we're going to have to bring in another factor, which is length contraction. But if he watched his twin travel away in a telescope, his clock is now slowing down by the Lorentz factor. The Lorentz factor at 95% is 3.2. His clock has slowed by 3.2. As he sees him approach the distant galaxy, 10 years hasn't elapsed on the moving clock. Only 3 years has elapsed on the moving clock. And so when it comes back, 21 years hasn't elapsed, only 2 lots of 3.2. The moving twin returns, and he only has aged, he's only 36. And the twin that stayed at Earth is 52. Now this is a paradox because that was just from twin number 1's frame of reference. If you put yourself in the astronaut that travelled away, it did actually take him, length contracted. He would see the other twin's clock ticking slower. So if you flip your frame of reference, the other twin ages. There is a solution to this. It involves that pesky accelerating frame of reference. We didn't consider that twin had to accelerate up for quite a long period of time and then decelerate and then change direction, re-accelerate. So there are solutions to the twin paradox, but again, it's beyond the syllabus. I would like us now, I've got 15 minutes and I apologise that I've been talking for so long, but I've got to get you guys ready to do some work next lesson. Muons, okay, we don't see trains whiz past at 85% the speed of light, okay? But Muons are little energetic particles that are created in the upper atmosphere. They are collided by a cosmic ray and they are produced. Now, a muon has the symbol mu, all right? It's like a heavy electron, all right? We will learn in the standard model, it's a negatively charged particle. And muons in the lab at rest, they have a decay time of 2.2 microseconds. They only last, when they're stationary, for 2.2 millionths of a second, and then they decay down into lower leptons, electrons and antineutrinos. When they're made, they are created with a velocity around about 99% the speed of light. All right, so their V on C term, their beta term is what it's called, but the V on C term is 0.99. Now, they're up in the upper atmosphere. So in the upper atmosphere, we are talking around about 10,000 meters up, all right, where the atmosphere is thin enough and the cosmic rays can come down and strike particles. Classically, they should only last for 2.2 microseconds. They should only travel a distance of their speed multiplied by their mean half-life, 2.2, which becomes 600, around, I'm going to write around about, just so it agrees with the diagram. They should only really travel 600 meters. Which means, if you're created 1,000 meters up, 10,000 meters up, most of them, half of them decay 650. Theoretically, none of them should reach Earth, right? Because they should decay before they manage to travel down to the Earth's surface. However, they are observed to reach the Earth's surface because we are watching this muon. We observe a measured time. That is the muon's clock. So the muon has his own clock and it's ticking down. Oh no, it's 1.1 microsecond. Oh no, it's 2.2. And then they decay when their clock reaches 2.2 microseconds. I know. We don't observe 2.2. We observe a moving time. So this bloke down here goes, oh, hang on, I don't see that. I see the muon's clock ticking slower. All the while it's travelling at 99% the speed of light. It's ticking slower by the Lorentz factor, which comes out to be, let's write out the whole equation just while you're new to the thing. 2.2 outspits 15.6 microseconds. All right? So again, imagine you're an observer at sea level with a telescope and you're looking at your stopwatch. It's counting up 4 microseconds. The muon's clock only says 0.5. 8 microseconds, the muon's stopwatch only reads. But in 8 microseconds, it's travelled more than 650 metres. You think, holy crap, 15 microseconds, his clock's reading 2.0. It's travelled about 8,000 metres in that time because it's lived for longer than 2.2 microseconds. By the time it reads 15.6, it smacks into the Earth. Let's take that observed time and find out an observed length. So we'll go, we don't see the muon travel 650. We see the muon travel a lot more. And so these muons have actually been detected at the Earth's surface because special relativity says that moving muons have slower clocks. Okay? Now that's their half-life, remember? So obviously not all of them get down to the surface. Some of them might have perished, but many more get down. So if special relativity didn't work, we should not expect to see any muons striking the Earth. With special relativity, you could figure out the percentage that reaches the Earth's surface, and sure enough, they do. Now, do we have 10 minutes left? Good, good, good. An interesting thing occurs. Boys, if we observe something moving, then we measure the proper length, but we see the consequences that their clock ticks slower. We see time dilation. But let's look now from the perspective of the muon. if the muon lived for, his clock says that he lived for 2.2 microseconds, but he got down to Earth. So he didn't see himself travelling 4,700 metres. He saw that length compressed or contracted by the same ratio that the time was dilated. So from the muon's perspective, if his time is proper, then the length that he travelled in that time must have been contracted. This is known as length contraction. There is a second equation in your data sheet. We'll just write it here, length contraction. That is a G and an N, length contraction. Now, here's where it gets tricky. The stationary length, we're going to say that L naught is the stationary length, or the length measured in the same reference frame, okay? And L is going to be the observed length. So this is going to be the length that the muon observes. Now the muon observed that length with a proper time t naught. The stationary observer at sea level saw a measured time with the proper length. So we're going to link T with L proper and T proper with L. That's the key here, and you'll see that you get an inverse. So we will go that L equals V times T proper. We'll get that L naught equals V times T. And if your velocities are the same, then we can simply make a ratio. We can say that L on T naught equals L naught on T. You could say L on L naught equals T naught on T. Well, that's just the inverse of gamma. That there, if I just took my time dilation equation and flipped it, we've got the inverse of gamma. That's what I was saying. The length is shortened by the same factor that time is dilated. And so when we throw in our L equals L naught times 1 on gamma, then you're going to go 1 over the square root of blah, blah, blah. You end up with the following. L equals L naught square root 1 minus V squared on C squared. So that is in datasheet.
You don't really need to know those derivatives.
No. Just you use those equations and you throw the values in. So let's just go back to, sorry, I hope you've written that down. Just look at the diagram. These are two different reference frames. So the muon's reference frame said, no, my time was correct, but I saw the distance that I was travelling contracted by the same factor. So what was the factor? I didn't work it out. It was about 8-ish. It was contracted by 8. So the muon said, no, I travelled 650 metres and I lived for 2.2 microseconds. It's just that it was 4,700 was contracted into 650 metres. The person on Earth said, no, I saw that muon travel the full length, but the time was dilated. So you can shift from one person's frame of reference to another. You either get time dilation or length contraction, okay, from each person's frame of reference. So, did I write that moving clocks appear to tick slower and moving sticks appear shorter? So, in this box over the page, could you please write moving rulers, let's just say rulers. Okay? So you take a meter ruler and you're at rest with the meter ruler, you measure it to be a meter ruler. That meter ruler then whizzes past you at 95% the speed of light. It would look like a little 15 centimeter ruler. Okay? But from the meter ruler's perspective, he is a meter, and you would see a very skinny Mr. Murray receding past in the opposite direction. Again, it's paradoxical. So, if in that box we place that moving rulers appear shorter, then I want in the time dilation box on page 16 that moving clocks appear to tick slower. So could we just go back to remember those two statements? Oh, wait. Did I put that statement for the length? Ah, well. You've got it written there. So let's just say your t, in this case, is going to be greater than t proper. So time dilates if you observe a moving clock. Length contracts if you observe a moving ruler.
Which one's proper again?
So the measurement taken in the same reference frame.
Yeah, so which one's that?
Well,
Which T is that again?
T naught.
Yeah,
In the case of the length, the reference frame of the actual muon isn't correct. The reference frame is present standard.
Well, when we measured that mountain in that diagram, we were probably at rest with that mountain, and we said, all right, that's 4,700. When the muon whizzed past it, it didn't measure L proper. It said that mountain looks 650 metres. All right, so that was not the proper length. That was an observed contracted length.
So you've like switched around which reference frame is
Switch them around, yeah.
Sure.
Yo,
If you had like a train on some train tracks going like at like 0.4 speed of light, what would happen for like wear and tear? Because you've got two different like frames of reference for time, which would affect how the wear of the
Everyone else in Beijing.
track.
that's the weird thing about it. If you suddenly, boys, this is the strange thing. This is the paradoxical nature of non-simultaneity. If you jump into somebody else's reference frames, then your observations do not agree. That was the whole thing at the start of the lesson. In a different reference frame, that person says that the lights flashed at different times. The other observer says that they flashed at the same time. We're not ever going to be able to quickly do a reference shift. We're never going to be able to suddenly shift into the train and out of the train to see that those observations were different. We're always going to be stuck in one. So we always see the muon live longer. We don't get to see that as the muon travelled, all of its dimensions were squished. Oh, one last thing. The length contraction is in the direction of the motion. So, look. No, I do want you to write it down. Go back to your length contraction box. Page 19. Here's our spaceship. If our spaceship was travelling this way at 0.99 c, then the y dimension is not contracted. It is only the x dimension. All right? So the...
It's perpendicular, right? They don't change.
So it's only the x length that is contracted. So you could say moving rulers are shorter in the direction that they are travelling. Okay? So I think that I've thrown in a question into your booklet. You'll work through some questions tomorrow. If I give you a spaceship of 3 dimensions, it's only going to be contracted in the direction that it's travelling. All right?
Increases density, that's possible.
Yes. That means its mass increases.
No, it's massively constant.
Well, no. Its momentum is going. We'll look at that on Friday. Yes. All right, guys. Thank you for listening to me for a whole 50 minutes. Tomorrow's lesson, you'll be working through questions. Good luck. God bless.